This may be counterintuitive, but studies have shown that shallow banding can actually increase nitrogen loss to volatilization. Shallow banding may occur when seeding a shallow-seeded crop like canola, or when the producer is trying to reduce the draft on his implement. But before we talk about that, let's quickly review how we lose nitrogen from our soils. When urea converts to ammonium, ammonium can potentially convert to ammonia, which gases off into the atmosphere. Ammonia is not a greenhouse gas, but losing it's not economical. Urease inhibitors, such as NBPT found in agrotane, Anvil, and Super-U, can reduce these losses by slowing the conversion of urea to ammonium. Anvil also has duramide to help improve the effectiveness of the NBPT. Ammonium converts to nitrate, and then the nitrate can be lost to denitrification under waterlogged anaerobic conditions. Essentially, the soil bacteria are using the nitrate as an oxygen source when they can't breathe. This produces dinitrogen gas, which is not a greenhouse gas. Our atmosphere is 78% dinitrogen gas. However, denitrification also produces nitrous oxide, which is a greenhouse gas of concern. Nitrification inhibitors such as DCD and Super-U and nitropyrin in Entrench protect against denitrification loss by slowing the conversion of ammonium to nitrate. So, why can shallow banding result in more volatilization of ammonia than even a broadcast application? Well, the concentrated band of urea raises the pH of the surrounding soil, which drives ammonium to ammonia, which is then lost to volatilization if there's not enough moist soil above it. Banding products containing a urease inhibitor can reduce volatilization losses and, in turn, yield losses from shallow banded urea. If urea is banded deep, i.e. 4 inches before packing, then using a urease inhibitor rarely made a yield difference. However, products containing a nitrification inhibitor have still been observed to reduce nitrous oxide emissions without resulting in a yield benefit. There are two reasons I can think of for this. One, nitrogen losses through denitrification were significant, but not large enough to have an impact on yield. Also, there may have been more than adequate soil nitrogen for the season, so a modest loss of nitrogen still didn't affect yield. In this study, there's a high and low rate of nitrogen to improve the chances of detecting an impact of N loss on yield. Also, we're using wheat, even though shallow banding is more likely to be common with canola, because with wheat, we can use yield and protein as an indicator of any N loss. The comparisons are broadcast, shallow banded, and deep banded applications of urea versus Super-U. I wish we could have also included an agrotane or an Anvil because these products may have provided better protection against ammonia volatilization. The nitrification inhibitor in DCD in Super-U may result in actually more ammonia volatilization compared to agrotane by keeping the nitrogen in the ammonium form for longer. However, ammonia is not a greenhouse gas, and Anvil and agrotane don't prevent the loss of nitrous oxide. So, the focus has been on products like Super-U. Having Anvil for comparison would also help us determine if any N loss affecting yield was also due to volatilization or denitrification. There are no nitrous oxide emissions being measured in this study. We are solely measuring the effects of management on yield and grain protein, and we'll assume that any differences are due to differences in N losses. Producers should understand how management can affect N-use efficiency. Economically, I suspect deep-banded urea to provide the best economic returns. This study was conducted by the following AgriArm research groups located in Yorkton, Prince Albert, Scott, and Milford. Here are the main effects of product placement on wheat yield at each location. At Yorkton, Prince Albert, and Milford, differences in yield could not be detected, whether nitrogen was broadcast, shallow banded, or deep banded. At Scott, there was an interaction between product placement by nitrogen rate, which I'll elaborate on soon. But I also want to point out that differences in yield could not be detected between applying straight urea versus Super U at any location. However, all locations were significantly responsive to added nitrogen. Increasing the rate of soil plus fertilizer N from 80 to 160 pounds per acre increased yield at Yorkton by 11.2%, at Prince Albert by 5.9%, and at Melfort by an impressive 28%. Now at Scott, there was an interaction where yield only significantly responded to added nitrogen when it was broadcasted and not when banded. At first, this seems counterintuitive until you realize the yield at 80 pounds of nitrogen per acre is significantly lower when broadcasted compared to banded. For this to happen, the nitrogen from broadcast applications must either be stranded at the surface or was lost to volatilization. While increasing nitrogen rates to 160 pounds per acre was still sufficient to maximize yield for the broadcast applications, it's not sufficient enough to maintain grain protein relative to the banded applications. So there was less nitrogen available to the crop when broadcasting, which I attribute to volatilization, since using Super U over urea significantly increased grain protein, but only for broadcast applications. There's no evidence here to suggest volatilization losses were high when shallow banding or deep banding. Let's check out the protein results from the other sites. Grain protein increased significantly in response to added nitrogen at every site, but a number of sites had significant interactions, except for Prince Albert. So that's the end of the story for Prince Albert, as neither product placement nor product significantly affected grain protein, and there were no interactions. For Scott, we have already discussed the interaction that showed Super U reduced nitrogen volatilization for only the broadcast applications. At Melfort, there was a significant product placement by nitrogen interaction, which we will check out first before examining the three-way interaction at Yorkton. While increasing nitrogen at Melfort increased grain protein for all the methods of product placement, the increase in protein was greatest when product was deep banded. This implies that deep banding had the highest end-use efficiency and less nitrogen was available to increase the protein when product was either broadcast or shallow banded. While this supports the hypothesis that volatilization losses would be higher with broadcast and shallow banded applications, using Super U for these applications didn't increase grain protein as would be expected. So we are lacking some key evidence to support volatilization loss, despite there being 8 days available for volatilization to occur before sufficient rainfall was received to move the nitrogen into the soil. But let's move on to Yorkton, where we did see some benefit from using Super U for broadcast and shallow banded applications. At Yorkton, there was a significant three-way interaction between product placement, product, and nitrogen rate. So now we have to look at all individual treatment means. Watch my scale here. It only runs from 13 to 16% protein. I don't want you to think the protein differences are super large. When fertilizer was broadcasted and left on the surface, Super U resulted in significantly more grain protein for both the low and high rate of nitrogen. It appears broadcasted Super U was able to prevent some volatilization losses before 19.4 millimeters of rain was received 7 days after application to move the fertilizer into the soil. When products were shallow banded, Super U provided significantly more protein when compared at the high rate of nitrogen. However, the opposite was the case for the low rate of nitrogen, though technically these levels are not considered statistically different. When deep banding, protein levels were identical at the high rate of nitrogen. When comparing at the low rate, Super U unexpectedly produced significantly less protein than straight urea. So there is some inconsistency with the results. However, if we focus on the high rate of nitrogen where the highest N losses would be expected, there was a significant benefit to using Super U when broadcasting, shallow banding, but not when deep banding. This implies the Super U may have stopped some volatilization losses associated with broadcasting and shallow banding, but was not required when deep banding. This supports the results of what past studies have observed. For the most part, Super U would not have paid for itself based on the results from this study. But if we take the best case scenario from Yorkton, we would require a protein premium of 38 cents per percent per bushel just to break even. So, in conclusion, there was some evidence to suggest volatilization losses were higher when broadcasting and shallow banding, and that these losses could be reduced by either deep banding or using Super U. However, using Super U over straight urea would have only been economical at a protein premium of 38 cents per percent per bushel or beyond. Thanks to the SCAP program for funding this project.